Good morning, children. Today we'll discuss about effective area or effective aperture. Let us go with the presentation. Effective aperture or effective area, which is represented with capital A suffix E. So generally antennas may be used for receiving or transmitting the electromagnetic energy, and here this effective area which is related to the receiving antenna. So the effective aperture is nothing but the effective aperture is the ability of antenna to extract the energy from the electromagnetic waves. It is also called effective area. So effective aperture is defined as the ratio of the power received in the load to the average power density produced at the point. So P received by P average square meters. So power received by the antenna may be denoted as PR, and it is power received is measured in watts. Power delivered is measured in watts per square meter. Watts per square meter. So effective aperture is measured in square meters. So we can say effective aperture can be explained in other words as the area which extracts the energy from the electromagnetic waves out of the total area of the antenna. If we consider the total area of the antenna, this effective aperture is nothing but the area which extracts the energy from the electromagnetic waves out of the total area of the antenna. So antenna should have the maximum usable area to extract the energy. So thus maximum effective aperture is obtained when power received is maximum. So this is denoted by AEM. In general, antenna has certain impedance which is made up of resistive and reactive part. So antenna has a impedance which is made up of resistive part and reactive part. So resistive part of the impedance is nothing but the radiation resistance, which is represented with R red. So this condition is true because same antenna can be used for the transmitting or receiving the signals. Now power transferred will be maximum if the load connected to the antenna is complex conjugate of the antenna impedance. That means here when we are sending a power, so it will be maximum if the load connected to the antenna is complex conjugate of the antenna impedance. Let us see. So let us calculate the effective aperture for the Hertzian dipole. So when the Hertzian dipole is receiving antenna, here we are considering the Hertzian dipole as a receiving antenna. It extracts the power from the incident waves and delivers it to the load. And here Hertzian dipole, it extracts the power and it extracts the power from the incident waves and it delivers to the load. And here and then producing the voltage in it. So here this is the circuit, and here this is the load, and this is the impedance R red plus jx, and here load we have connected is complex conjugate of the impedance part. So ZL equals to R red minus jx. Here printing is not there. ZL equals to R red minus jx. This is the impedance. Z equals to R red plus jx, and here voltage can be produced. This is the circuit of the receiving antenna. So voltage induced in the antenna is given by voltage equals to mod A dl. So E is the magnitude of the electric field intensity which is producing the receiving point, and dl is the length of the Hertzian dipole. So current flowing in the load is given by I equals to volt by Z plus ZL. So for the maximum power transfer condition, load is selected as a complex conjugate. Already we have seen load, already we have seen complex conjugate of the antenna impedance ZL equals to Z, and substituting the value of impedance Z and ZL, the current flowing can be written as I equals to voltage by Z plus ZL. So R red plus Jx plus R red minus Jx. This is the complex conjugate of this impedance. So I equals to VOC by 2 into R red. So this when we they get cancelled, so we'll obtain 2 rad. So then power delivered to the load is given by power is equals to I square RMS R rad into voltage by 2 rad by root of 2 whole square rad. So IRMS in electronics I by root 2 value. So IRMS value in electronics I by root 2, and here so power delivered to the load is given as I square RMS R rad, which is equals to VOC by 2 rad by root of 2 whole square into R rad. That means here I square I value is this one within the bracket VOC by 2 rad by root of 2, and R rad we are writing here, and in electronics IRMS equals to I by root 2. So here we are considering this one as I by root 2. So PR equals to VOC V square by 8 into R rad. So and here by squaring 2, and we will obtain this one. So substituting the value of voltage from equation number 51, we will obtain PR equals to E square dl square by 8 R rad. So maximum effective aperture is given as AM equals to maximum power received to the average power density. So PR maximum by P average. So AEM equals to, so PR maximum already we have E square dl square by 8 R rad by power average, which is equals to half E square by eta naught. So AEM equals to DL square by 4 rad into eta naught. So substituting value of R rad and eta naught we will obtain. So AEM equals to DL square, eta naught value equals to 120 pi into 4, R rad 80 pi square DL by lambda whole square. And by solving we will obtain AEM equals to d lambda square by 8 pi. So by cancelling we will obtain this one. So AEM equals to diet equals to here 1 point. So here by solving this one, we will obtain 1.5 into lambda square by 4 pi. So this equation represents the maximum effective aperture of the Hertzian dipole. But the directivity of the Hertzian dipole we have standard value 1.5, and hence we can rewrite the expression for the maximum effective aperture is here. So Hertzian dipole directivity, it is represented with GD maximum, which is, so AEM equals to, in the place of 1.5 we are replacing with GD maximum into lambda square by 4 pi. This is about effective aperture. Thank you, children.